Hey guys, it's Piggy Puncher here. There's a lot of confusion and misinformation surrounding active radar missile mechanics like angle gating, notching, and their seeker modes, as well as how to optimally defeat these missiles. Like, sure, we know about flying perpendicular, dropping chaff, and maneuvering to defeat the inertial guidance, but how do missiles actually work under the hood? It doesn't help that Gaijin is notoriously non-communicative about these critical mechanics on how their game works. So I ran way too many tests with some friends to figure out how these mechanics are actually implemented and found some very useful and actually interesting results. In this video, I'll be explaining how active radar missile seekers work. More specifically, I'll be answering these key questions. 1. How is radar cross-section implemented in-game? 2. What seeker modes does an active radar missile have? How does each one behave, and what triggers the seeker to switch into different modes? 3. How does chaff work, and how are the different calibers of chaff implemented in-game? 4. How do radar seeker filters work, like the angle gate and the notch filter? And 5. What are the main differences between specific active radar missile seekers, in particular the MICA and the Phoenix variants? Quick disclaimer, it's impossible to know exactly 100% how these missiles actually work since we can't access Gaijin's code, so this is basically my own opinion on how these missiles work, but I'll describe what tests I ran to arrive at these conclusions. I'll also assume that you have a very basic understanding of how notching and radars work. If you don't, then go watch my previous video on the subject. So, War Thunder does seem to model RCS in-game, but its implementation is extremely oversimplified, and in most situations it doesn't really impact gameplay in a significant way. We used the weak radar on the interceptor Vautors to see at what ranges a target could be hard-locked, and found that the IL-28 can be locked at a much longer range than something like an HE-162, confirming that there is some kind of aircraft size-based RCS calculation. Next, we found that the HO-229 can be locked at longer ranges than the F-104, not only in front aspect, but also in the side aspect, even though the HO-229 side aspect profile is slimmer than the F-104, indicating that RCS is likely calculated based purely on aircraft wingspan. Finally, we found that there is very little difference between lock ranges for the HO-229 flying purely side aspect versus side aspect banked at 90 degrees to expose the whole wing area, indicating that the game likely doesn't differentiate between top-down and side-on. The Datamines seem to support this, as in one of the files defining general parameters, there are only multipliers for front, side, and rear aspect, none for top-down. So my working theory for how RCS is calculated is that for any aircraft, the RCS is the shape of an elliptoid, formed first by taking a sphere with the diameter equal to the aircraft's wingspan, then stretched and squished based on the multipliers. This results in an oblate spheroid with a fat midsection for most planes, with the exception of stealth aircrafts like the F-117, which have different multipliers explicitly enumerated in their FM file. Knowing how RCS is calculated isn't critical to know how missiles behave, and the variation isn't large enough that it matters, especially at top-tier ARB, where radars are strong enough to see targets from hundreds of kilometers away, but I thought I'd include it since the results from the next tests are just tested with specific airframes, so they will vary somewhat depending on conditions. Before we get into the details on how missile seekers work, it's good to know that almost every active radar missile seeker in-game have identical parameters when it comes to their radars. Their main difference comes from their motor, guidance computer, flight performance, and warhead properties, but not their radar, so these results should apply to all Fox-3s in games. The two major exceptions are the Phoenix variants and the MICA, which we will address separately. So, there are three main active radar missile seeker modes: Doppler, Pulse, and inertial guidance. Doppler is the primary mode that the missile uses to guide itself in by detecting the velocity at which the target is approaching or retreating from the missile. It has two filters: the notch filter, which filters out signals approaching at the similar rate to the ground to remove ground clutter, and the speed filter, which filters out new signals that have a different approach speed from the target. This is used to filter out chaff, since chaff slows down very quickly, becoming stationary almost instantly. So the main behavior of Doppler mode is that it is basically immune to chaff and holds lock very consistently at most relevant distances, but is susceptible to being notched. When the seeker notices the target go into a notch, it tries to switch to pulse mode. There's a lot of details to talk about regarding this mode, but in essence, this seeker is susceptible to both chaff and ground clutter because it doesn't have Doppler-based speed filters. If it sees chaff, it will go for it. If the target exits the notch, the Doppler seeker takes over again. But if the target is notching to defeat the Doppler seeker and there's too much ground clutter for the target to be picked up by the pulse seeker, the missile switches to inertial guidance. So inertial guidance is used when the missile seeker cannot find the target either in Doppler mode or pulse mode. when the target is notching and there's too much ground clutter to pick the target up in pulse mode. While in inertial guidance mode, the missile will try to search for and predict the trajectory of the target using information based on the target's last known position, speed, and direction. Data link from the aircraft radar can be used to direct the missile where to look for the target, but I'll get into data link in a different video. If either the Doppler mode or pulse mode picks up the target, whether because the target leaves the notch, the target climbs above ground clutter, or the missile gets close enough to burn through the ground clutter, then the seeker exits inertial guidance and resumes tracking. Of these three seeker states, the most interesting is the pulse mode, as it comes with a lot of unexpected behaviors. First, it's actually very weak and picks up a lot of ground clutter even when it is looking above the horizon. To get a better idea of at what point the missile can detect a notching target by burning through the ground clutter, we ran a bunch of tests with an attacking aircraft launching missiles and a defending aircraft maintaining a notch at various altitudes and observing when the missile switches from inertial guidance to track. And here are the results. We have the attacking aircraft's altitude listed at the top, the defending aircraft altitude listed on the left, and the numbers indicate the range from the defender that the missile went into track. So with the attacker at 6 kilometers and defender at 4 kilometers, the missile only detects the defender when it's 0.9 kilometers away. These circles indicate that the missile goes into track as soon as it goes active at 16 kilometers from the target, and these X's indicate that the missile never goes into track and remains in IOG. We can also reorganize this data to distinguish between how far above or below the horizon the missile is looking. Doing so makes it very clear that unless the missile is looking significantly upwards by at least 6 degrees above the horizon, the missile is not going to detect the defender until it gets within a range of 5 kilometers. And true lookup mode only really starts with at least a 13-degree launch upwards for the pulse mode to detect notching targets at max range. Another important takeaway is that the closer to the ground the defender is, the closer the missile has to be to detect the defender. If the defender is very close to the ground and stays in the notch, then the missile will basically never find the target and remain in inertial guidance the whole way through. Now, how do these results change when we add chaff to the mix? Since pulse missiles like the R3R always get one chaff, I think we can safely assume that chaff generally has a larger RCS than aircraft, so we'd expect it to get detected at longer ranges than the aircraft. Testing in look-down mode 6 degrees below the horizon at 10 kilometers altitude using aircraft with roughly similar wingspan so that they have roughly similar RCS, we can see that it actually picks up and detects chaff from longer ranges even when it's in IOG. BOL chaff gets picked up at 3.3 kilometers, standard caliber chaff gets detected at 3.7, and large caliber chaff gets detected at 5 kilometers. So it seems that chaff caliber does actually make a difference. Having more chaff launchers does not increase the range at which the chaff gets detected, so whether you have 1 BOL pod or 4 BOL pods, the range at which chaff gets detected will still be 3.3. And just to be clear, these ranges are not universal and apply only to the conditions in which these tests were run. If the missile was launched at higher lookup angles, chaff would be detected at longer ranges. The main point of this test was to show that chaff gets detected at longer ranges than the aircraft due to its larger RCS. I'd run these tests at different altitudes and aspects, but that'll probably take a really long time, so I think for now it'll suffice to say that you can probably just look at the table for the aircraft detection range and multiply that number to get a fair estimate of chaff detection range. The better performance of larger caliber chaff is reflected in the Datamines, where almost all of the parameters for chaff of different calibers are exactly the same, with the exception of this multiplier value, which is 0.05 on BOL chaff, 0.2 on standard, and 1.1 on large caliber chaff. We also tested to see if the direction that chaff gets deployed matters. All chaff countermeasures start with an initial velocity of 70 meters per second relative to the aircraft, but very quickly decelerate to being stationary almost instantly. To test if this brief speed makes a difference, we used the Kafir, which has chaff dispensers that point purely sideways, to see if the missile would be more sensitive to chaff deployed directly towards the missile seeker. But this gave the same result as the standard caliber chaff at being detected at 3.7 kilometers, so the direction that chaff gets deployed doesn't really seem to matter. Now in these tests, even though the missile detects the chaff, the seeker ignores it and continues to guide itself towards the aircraft. This is angle gating in action. The way that it works in theory is that when the missile is following a target and detects a new signal, it compares how quickly the new signal moves across its field of view compared to the old one, and if the new signal moves across its field of view at a significantly different angular velocity compared to the main target, it ignores the new signal and forces the seeker into inertial guidance temporarily before resuming its previous tracking. This allows the seeker to ignore chaff when the target is in a notch, since the target will be traveling across the missile's field of view at a significant angular velocity, but chaff will decelerate and become stationary almost instantly, giving it a significantly different angular velocity which the seeker notices and uses angle gating to ignore. To confirm this theory, we ran some tests with the target in the notch and seeing at what range and velocity chaff would either successfully decoy the missile seeker or if angle gating would ignore the chaff. For an aircraft flying at 2000 kph TAS, the range at which chaff gets ignored by angle gating is around 7.7 kilometers and below. For an aircraft flying at 1000 kph TAS, the range at which chaff gets ignored by angle gating is around 3.8 kilometers and below. And for aircraft flying at 500 kph TAS, the range at which chaff gets ignored by angle gating is around 1.9 kilometers and below. So it seems that range at which angle gating kicks in is roughly proportional to the aircraft's velocity. Which makes sense, since the farther away from the seeker you are, the faster you have to travel in order to achieve the same angular velocity. To see if the datamines confirm this theory, I checked the angle gating values for each active radar missile, and all of them have this parameter set to 30, which I would assume is in degrees per second. Now, if we assume that this is the angle gating threshold, where it ignores signals moving over 30 degrees per second compared to the previous target, then an aircraft flying at 1000 kph should get its chaff angle gated and rejected only at 530 meters or closer, which is much lower than what our tests suggest. If we assume that 30 degrees per second is a two-direction bound, and so in one direction, the angular velocity threshold is 15 degrees per second, then an aircraft flying at 1000 kph should get angle gated only at 1060 meters or closer, which again is too close since we're expecting around 3800 meters or 3.8 kilometers. And after spending way too much time trying to figure out how this works, I stumbled on what I think is the actual implementation, which is a little odd. I think Gaijin either forgot to do unit conversions or intentionally just made this calculation without regard for units, but if we intentionally forget to convert aircraft velocity from kilometers per hour to meters per second, then we find that the calculations match our results almost exactly. So I'm pretty confident saying that this is probably how Gaijin implemented angle gating. So here's a graph showing how it should work based on our theory. An aircraft with a lower speed at a farther distance does not trigger angle gating, and so chaff will be effective at defeating the missile, while an aircraft with higher speed at a closer distance does trigger angle gating, and so the missile seeker would ignore the chaff and go into inertial guidance. Angle gating seems to work whether the missile seeker is actually tracking the target or if it's in inertial guidance and just guessing the target position. You can see here that even though the missile is already in inertial guidance and cannot see the target, it notices the chaff and detects that it is traveling at an angular velocity significantly different from the inertial guidance's predicted angular velocity of the target, so it just continues in inertial guidance while rejecting the chaff. Angle gating and inertial guidance in general does seem to be rather inconsistent though. There are some instances where the missile decides not to angle gate and just goes for chaff, and I really couldn't come up with a good explanation for this behavior. Well, now the natural next question to answer is, how long does the missile stay in inertial guidance when you chaff? To test this, we tried deploying periodic chaff at different rates to see at what rate you need to keep the missile in IOG. For most missiles, it seems like once per second seems to successfully keep the missile in IOG. This is where we need to talk about the MICA though. The radar parameters for the MICA is identical to most other missiles, with the one exception being that the transmitter and receiver's half-angle sensitivity being less than half of that of other missiles, 7 degrees instead of 15. Half-angle sensitivity is a measure of how narrow the missile's seeker's field of view is, meaning the MICA has a much narrower seeker FOV than all of the other Fox-3s. This makes the MICA harder to chaff, since chaff stays inside the seeker's field of view for a shorter period of time, and once the chaff leaves the missile's FOV, the missile exits inertial guidance and relocks back onto the target much faster than other missiles, similar to how gate-width IRCCM missiles like the R-73 and Magic 2 work. Running the same test with the MICA, chaffing once per second did not keep the missile in inertial guidance consistently enough to avoid the missile, but 1.5 chaff per second seemed to work. So the most important aspects of defeating angle gating is not necessarily how much chaff you drop, but when you drop it, how often you drop it, and what maneuver you're doing while you're dropping it. Time it right and pair it with the right maneuver, and 3 to 5 chaff should be enough to defeat most missiles, including MICAs. If the missile is close enough, you can even do it in 1. When you're in an actual battle, you still want to drop chaff at a higher frequency than 1.5 per second if you have enough chaff, since it is better to be on the safe side and be certain that you've defeated the angle gating. though you probably don't need to spam it off nearly as often as Megan does in his video on defeating close-range Fox-3s. Personally in-game, I found that 3 chaff per second works quite well in terms of consistently defeating angle gating while being economical, which is nice when playing planes with small countermeasure counts like the new Norwegian F-16 Also, it seems like it is not more difficult to physically get into the notch band of the MICA. It's just that once you're in the notch band, it's harder to defeat the inertial guidance since chaff is effective for a shorter period of time. Speaking of notching, let's look at the notch filter in more detail. First, I want to make one thing very clear. The notch filter removes signals based on approach speed, the component of aircraft velocity pointed towards the missile seeker. Some people seem to think that it has to do with the angle that your aircraft's velocity makes with the missile radar, but that's more of a result of you trying to stay within the notch band. You can be stationary or even traveling very slowly directly towards or away from the radar and still be in the notch band if you're slow enough. But how slow is slow enough? What exactly is the width of this notch band? We tested this by driving a plane on the ground, firing a missile at it, and slowing down to see at what speeds the target has to be to trigger the missile to switch from track to IOG. In front aspect, the threshold speed seems to be pretty consistent, 144 kph or 40 meters per second, no matter the range. In rear aspect, the threshold speed was actually not one set value and seemed to change based on how far away from the missile you are. At longer ranges, we got the missile to go into IOG at around 360 kph or 100 meters per second, while at closer ranges we got it to trigger at around 270 kph or 75 meters per second. We couldn't test this extensively at all ranges, but the key takeaway is that the notch band seems to be heavily front biased, and it is much easier to stay inside the notch band if you keep your aspect a tiny bit cold as opposed to front aspect. This is probably another contributing factor to why when in a close range notch you have more success when you pull into a turn that looks like it's over 90 degrees on top of your aircraft drifting from angle of attack. Testing to see if these results are different in lookup mode was a bit trickier since there is no convenient ground in the sky that we can land and slow down on. We tried decelerating in VTOL planes, but in lookup mode the missile just switches from Doppler mode to pulse mode, which we can't distinguish in sensor view. Dropping chaff also didn't seem to help since the plane wasn't moving much, making it difficult to see when the missile switched targets. So what we ended up doing was flying at an imperfect notch, slightly front aspect enough not to fall into the notch band, then slowly angling into the notch band and seeing at what angle the missile starts to detect chaff. Then, based on that angle, we can calculate the component of aircraft velocity in the direction towards the missile seeker by taking the dot product to see at what approach rate the plane was at when the missile detected the chaff. This method is probably pretty imprecise because it relies on small deviations in the aircraft's flight trajectory, but it's the best we got, so take the results with a grain of salt, but the result was an approach rate of around 90 kph or 25 meters per second. Even if this result is very imprecise, I think it's a clue that the notch band is narrower at higher lookup angles. We would have run this test at different ranges and also in cold aspect for the sake of completion, but this process for testing was very tedious to set up and do multiple times in a consistent way, so I don't mind stopping here for now and maybe coming back to this later, and for now concluding that the missile's notch band is likely narrower the more lookup it is. Since we don't have much data collected on this, I also don't have a good idea of how Gaijin's code implements the notch band, especially since it relates to ground clutter. But I do know that it likely has to do with this block of parameters, and since the MICA has the same values for these parameters, it's likely that the MICA is just as easy to get into the notch band as other Fox-3s. Just harder to defeat the angle gating once you're in that notch band. And now we have to talk about the Phoenix variants, which are the most unique Fox-3s currently in-game. First, there are some things that we can infer from the datamines, and others that we can conclude from in-game tests. Let's start with the datamines. The Phoenix radars seem to function fundamentally differently from other Fox-3 radars, as they lack certain parameters in their file that define other Fox-3s with PD radars. In particular, this distance and distance gate section. Next, their transmitter and receiver angle of half sensitivity is narrower than other Fox-3s, meaning that it has a tighter field of view. This would imply that it requires more frequent chaffing to defeat Phoenixes once they get close enough into angle gating range, similar to the MICA, but I haven't really tested this. And third, the inertial guidance drift rate is 5 times higher than other Fox-3s for the AIM-54A and Foghorn 90, meaning that in pure inertial guidance, the missile just tends to drift away from the target, which is not great if you can't data link them before they go pitbull. And now for the in-game tests. First, the Phoenix's pulse mode seems much weaker than other Fox-3s. We ran tests launching the Phoenix from the deck at different angles to see at what range it could lock a notching target, and the lock ranges are much worse than other Fox-3s. We would have tested this at more altitudes like we did with the other Fox-3s, but the F-14 radar is really bad at holding lock on targets close to the notch, even when we set up an off-angle shot, meaning no data link and relying on the crappy inertial guidance on the Phoenixes. Either way, the Phoenix is much worse at tracking notching targets. My hunch is that this is because the Phoenix has less side lobe attenuation than other Fox-3s, meaning its radar power is sent less to the main beam and more to the side lobes, which is also why the Phoenix can be really noisy and ping RWRs on nearby planes that it isn't actually tracking. Secondly, the Phoenix seems much more chaff sensitive at longer ranges. Not sure why, but even in lookdown and IOG mode, it seems to go for chaff quite readily as long as it's not angle gating range. Finally, and probably most importantly, the Phoenix is horrible at tracking cold aspect targets. We tested firing on targets that were in pure rear aspect running away at over Mach 1, and even at shallow lookup angles, the missile goes into inertial guidance, staying in inertial guidance until the missile actually got pretty close to the target. The key thing that we noticed here is that the missile starts in track, but then goes into inertial guidance as it accelerates, and the point at which it switches is when its speed is around equal to that of the target, when the missile's closure rate goes from negative to positive. My guess as to why this is happening is that because of the missing parameters in its file relating to distance and distance gate, the radar behaves like an aircraft's pulse Doppler velocity radar, and not a full pulse Doppler radar. PDV radars exhibit the same behavior of an increasing ground clutter band with increasing speed. Well, that's just about everything I wanted to cover for now. With this degree of depth of information, it might be daunting to try and remember everything and actually put these ideas to use in battle, so if you'd like, I'll try to do a more in-game battle-focused video showing how I approach each of these engagements with these concepts in mind. I'll also likely be doing another video on data link, RWRs, and other miscellaneous topics that I've already done some testing on, but I think this video is long enough as is, so I'll call it here for now. Hopefully you can understand why this video took so long to make. What I'm not including in this video are the hours and hours worth of tests that led nowhere and the brainstorming of theories that we ended up scrapping, so I hope that this effort was worth it and you find this helpful. If you found this information helpful, make sure to show your appreciation by giving your thanks to the people who helped me actually test all of this stuff. Some of them were less than excited when I asked them for help for the 12th time in a row after running a bunch of tests that ended up being useless, and especially so when our replay footage got nuked when they dropped the update, but despite everything they decided to still help me nonetheless. Also, special thanks to Carlos for working through brainstorming these theories on how these mechanics work together, as well as providing much needed contextual insight that he's gathered from playing his games in competitive tournaments. There's a good chance I'd be spreading actual misinformation in this video if Carlos didn't correct me on some of my own misconceptions. If you're interested in trying out for a competitive team or would like to join his community, consider joining his team's Discord server. But that's everything for this video, and I'm finally free. Yippee! Anyways, bye-bye.
Everyone shut up. Dubert has something to say. He is full of rage.